The topic of the month for April is Angle of Attack Awareness. The purpose of this presentation is to review the aerodynamics of angle of attack, present information on the benefits and use of angle of attack indicators installed in general aviation aircraft, and to help promote safe flying by raising awareness of angle of attack and reducing the likelihood of a loss of control accident. Angle of attack is defined by two references. One is the chord line of the wing, which is an imaginary line drawn from the leading edge to the trailing edge of the airfoil. The other reference is the relative wind, shown here by the red line. The relative wind is parallel to and in the opposite direction of the direction of flight. The angle represented by these lines is the angle of attack, or AOA. Reference angle of attack in the Airplane Flying Handbook, Chapter 4, Paragraph 4-2. Low angle of attack is typical of the cruise phase of flight. Relative wind impacts leading edge just below center. Higher speed of relative wind produces the needed lift, smooth airflow over the airfoil, stable flight characteristics, and responsive to control input. This AOA is typical of an airplane in cruise flight. The air separates cleanly just below the center of the leading edge of the airfoil, so it is not as disturbed as it flows over the top surface of the wings as it is with a higher AOA. The airflow is smooth over the airfoil, and the high velocity of the air over the airfoil produces the lift needed for level flight. In these conditions, the wing is stable and responsive to control input. High angle of attack is typical of approach and departure phases of flight. Relative wind impacts airfoil lower on the leading edge. Lift is produced by accelerated airflow over the top of the airfoil, feels less stable due to less responsive controls, and still a safe condition because the aircraft is still maneuverable and completely controllable. This is typical of lower airspeed operations such as approach or departure phase of flight. The relative wind impacts the leading edge further down from the center, so the flow of air becomes more accelerated, Bernoulli's principle, as it flows over the upper surface of the wing. The pressure difference is greater between the underside and the top of the wing, generating the lift needed for level flight. The airplane feels less stable because the flight controls are not as responsive and require greater amounts of input for a given reaction. This condition is still safe because the airplane is completely controllable and maneuverable. Regarding critical angle of attack or stalling AOA, not a normal phase of flight. Impact of relative wind moves lower on the leading edge. The air cannot smoothly flow from the leading edge to the trailing edge across the top of the airfoil, and the separation of the airflow results in the loss of lift, otherwise known as a stall. No matter how you reach this AOA, intended or unintended, this is not a normal phase of flight. While the reaction of the airplane is predictable, the pilot is not in control of the airplane in terms of being able to maneuver using control surface input until the AOA is reduced and the surface of the wing begins producing lift. Once the critical AOA is reached, there is always a cost in terms of loss of altitude that can only be mitigated by timely addition of thrust and smooth, accurate control inputs during recovery. The relative wind impacts the leading edge significantly below the center such that the airflow separates shortly after reaching the upper surface of the wing. The low pressure above the wing becomes a burbling air mass that is no longer attached to the surface and cannot produce lift. The critical AOA is an aerodynamic constant at which the airfoil will always stall. It does not matter if the relative wind is flowing at 60 knots or 200 knots. When the wing reaches the critical AOA, it will stall. It is important to understand that the critical AOA is an aerodynamic constant for a given airfoil in a given configuration. The velocity of the relative wind does not matter. The airfoil will always stall when the critical AOA is reached. The above is a practical description of the effect that is felt by the pilot of an airplane. We are all trained from the very beginning on what to expect and how to respond when we lower flaps. Viewed from the perspective of an aeronautical engineer, Lowering the flaps creates a completely different airfoil. All of the components have changed, including the actual critical AOA. We don't need to make a science project out of describing all the changes that just occurred for the purposes of this discussion, as long as we remain aware of how to maintain safe flight in the new configuration. As bank angle increases, centrifugal force on the aircraft increases as long as airspeed and altitude remain constant. Centrifugal force combined with gravity produces what is known as aerodynamic load factor and expressed as gravitational force, G-force, or G. As the angle of bank increases, G-forces increase so that in a 60-degree bank, the aircraft is producing 2 Gs. In other words, it effectively weighs twice what it does sitting on the ground. Thrust and angle of attack must be increased if altitude and airspeed are to be maintained during a steep turn. In a steep turn at a constant airspeed and altitude, the AOA of the wing is significantly closer to the critical AOA stall than in level flight. Reference Chapter 5 in the Pilot Handbook of Aeronautical Knowledge. Due to the increased aerodynamic loading of the aircraft in the steep turn, the wing is much closer to the critical AOA, and there are important things to be aware of. The increase in pitch angle may be much smaller than expected to stall the wing. The indicated airspeed at the critical AOA is significantly higher than in normal flight. The increased load, i.e. aerodynamic loading, of the airplane requires greater lift that can be created by increasing airspeed or increasing the AOA. Due to the increased aerodynamic loading, the stall sequence is condensed. The progression from indication to buffeting to fully stalled can be very rapid. Indicated airspeed may be up to 40% higher when the airplane stalls in a steep turn versus level flight. Note: we all have hopefully experienced the different characteristics in stalling an airplane we are familiar with in both lightly loaded and maximum gross weight conditions. If you have not experienced this, you should, because depending on the airplane, stall characteristics can be very different. Now, consider effectively doubling the maximum gross weight of the airplane in a steep turn, and you can see how the stall characteristics will be vastly different. Practice instructional flying at maximum gross weight is something that you might consider adding to your recurrent training routine when you go flying with your CFI to enhance your knowledge and ability, even in aircraft you fly on a regular basis. Pick 2 items like power on stalls and steep turns and fly short, back-to-back flights some afternoons so you can clearly experience the difference in the way your airplane responds. First, lightly loaded, then with a secured load within the weight and balance parameters of the airplane. If you do this regularly, you will not be so out of breath when you take a load of friends out for that $100 hamburger some late summer afternoon. Reference Chapter 4 of the Airplane Flying Handbook. This slide and the next slide are used in combination to show the difference in AOA being established in level flight versus steep turns, Block A. In level flight, to maintain altitude and maneuvering speed may require 8 to 10 degrees AOA, leaving 6 to 8 degrees AOA before the air separates from the wing and the stall sequence begins. In a steep turn, maintaining maneuvering speed and a constant altitude may require 14 degrees AOA, leaving only 2 degrees AOA before the stall sequence begins. Slips are not as inherently dangerous because the upper wing reaches critical AOA before the lower wing, causing the airplane to roll towards a wing level. Skids, on the other hand, are highly dangerous because the low wing reaches critical AOA first and the airplane rolls aggressively in the direction of the bank. The airplane will rapidly roll inverted or enter a spin. This is typical of the accidents resulting from a turn from base to final with a tailwind. The pilot should never try to push the airplane through the turn with excess rudder pressure. If you are overshooting final, it is time to go around. Note: all unintended stalls are dangerous. The statements above indicate a comparison between slips and skids. Regarding uncoordinated flight, skids, all unintended stalls are dangerous. Overshooting final is particularly fatal if a pilot uses excess rudder, forcing the plane into a skid at low altitude. Pilots seem to get focused on making the approach work out. Be aware of this and do not let your desire to land overcome your awareness of what is happening to the aerodynamic forces out on the wing. If you are turning from base to final with a tailwind and you are overshooting final, go around. If an airplane enters a skidding turn close to the ground, you're in a very dangerous situation. Note, to most certificated pilots, the aerodynamic condition of a skid is merely a theoretical condition. You may have demonstrated a skid at some point long ago, and most of us have a sense that they are not a normal flight condition and to avoid them. What we do not know is just how fast and at what point the skidding airplane moves past the boundary of safe flight into an uncontrolled state, because this was never demonstrated and it is arguable as to whether it should be demonstrated. The unfortunate part for many is that with a little extra pressure on the rudder, the boundary was exceeded. The human warning system here needs to be paid attention to, in that any time we are trying to make something work, there is always more going wrong than what we can immediately see. We need to fly smoothly out of the situation and come back and try it again, applying what we just learned about the conditions we are in. It is interesting how we break out into a cold sweat when we realize the dangerous position we put ourselves in yesterday. Wouldn't it be great if we broke out into a cold sweat just prior to putting ourselves in a compromised position instead? This is called good aeronautical decision making. The General Aviation Joint Steering Committee has recommended the use of AOA indicators as a means of reducing accidents in GA aircraft. In 2015, the following video was produced to provide a review of how AOA indicators work to enhance the pilot's awareness of the aerodynamic condition of the airplane.
This is an analysis of angle of attack devices in the general aviation environment presented by the Pegasus research team. The purpose of this video is to provide the general aviation pilot with information pertaining to angle of attack concepts, an overview of the benefits of angle of attack displays, demonstrations of several commercial angle of attack installations, and angle of attack display indications during typical maneuvers. To show why angle of attack displays have drawn recent attention, we will discuss loss of control accident case studies, safety enhancement analysis timeline, and angle of attack concepts. Then we will discuss what angle of attack devices are and how they function. We will cover angle of attack sensors and their functionality. We will highlight angle of attack displays by Alpha Systems, Safe Flight, and Bendixking. Finally, we will present how angle of attack displays can be beneficial in various flight conditions, including power-off stalls, power-on stalls, cross-controlled stalls, slips, steep turns, and approach and landing. In accident example number 1, the facts are that it was a Cirrus SR-22 flown by a private pilot certificated individual. The aircraft was on left downwind to land, and from the accident report, crashed into trees while turning base to final approach to runway 6 at the Aero Plantation Airport near Waxhaw, North Carolina. The weather was VMC, or visual meteorological conditions, and the pilot was operating VFR. Winds at a nearby airport reported at 310 degrees at 11 knots, gusting to 20 knots. The airport is described as tricky due to runway slopes and surrounding terrain. Here's an illustration of the flight path. As you can see, during the base to final turn, the pilot had a tailwind, and it's possible that the pilot initiated the base to final turn at the normal spot that they always do, which resulted in an overshoot and a potential for a cross-controlled stall. During the evaluation, the NTSB determined the probable cause to be the tailwind condition, which caused a ground speed higher than the airspeed during the base to final turn. To compensate for the increased turning radius due to the higher ground speed, the pilot increased the bank angle. The increased bank angle caused the stall speed to increase, resulting in a stall and subsequent loss of control. The NTSB determined the probable cause to be the pilot's failure to maintain adequate airspeed while maneuvering to land, resulting in an aerodynamic stall. This is the key part of loss of control in flight, where maneuvering flight is the top phase, where fatal loss of control in flight is most likely to occur. In the second accident case study, the aircraft was a Beechcraft Bonanza B-36TC flown by a commercial pilot. It was operating on instrument flight rules in IMC conditions. The aircraft was destroyed when it impacted terrain near Bunderon Airport, North Garden, Virginia. Ground scars and wreckage evidence were consistent with the airplane being in a spin at the time of impact. The site manager mentioned past flights in which he noted that the pilot had to make, in the manager's opinion, a sharp left turn to avoid terrain before landing on the runway. This is a picture taken from the final approach course, and as you can see, the terrain is varying and the pilot would need to modify the approach path. The NTSB found the probable cause to be the pilot's failure to maintain airspeed while turning onto the final approach, which resulted in an inadvertent stall spin and subsequent impact with terrain. In 2011, the General Aviation Joint Steering Committee, or GAJSC, recognized the need to address loss of control accidents and started researching ways to mitigate these events. They tasked the Safety Analysis Team with the analysis of accidents that were caused by loss of control. Following the Safety Analysis Team's findings, the Loss of Control Working Group was founded to research and make recommendations for potential solutions. The Loss of Control Working Group determined that angle of attack displays could be a useful mitigation strategy for general aviation aircraft. Following these findings, the FAA streamlined the approval process for various angle of attack devices, deeming them minor modifications to the aircraft which require less approval than major modifications. To better understand these devices and how they can be used, let's look at what angle of attack is. Angle of attack is defined by two references. One is the chord line, which is an imaginary line drawn from the leading edge to the trailing edge of an airfoil. The other reference is the relative wind, shown in this picture by the arrow marked airflow. Relative wind is equal and opposite to the flight path of the aircraft. The angle of attack is the angle between the chord line and the relative wind. The critical angle of attack is the point at which, as the angle of attack increases, air will no longer flow smoothly over the wing. When this happens, the airflow separates from the surface of the wing, resulting in a stall. The critical angle of attack, or the angle at which the stall occurs, is always constant for a given airfoil in a given configuration. Since the stalling point is only affected by the angle of attack, it is important to note that the wing can stall at any airspeed and any attitude. This is a wing with the flaps in the retracted position. When the flaps are extended, it changes the effective chord of the wing, which increases the angle of attack and results in a momentary increase in lift. To compensate for this new chord line, the pilot will normally adjust the elevator pressure to dissipate this momentary increase in lift to maintain altitude. The result is that an aircraft that has deployed flaps can produce the same lift at a lower angle of attack until the descent profile is initiated. Here is a graph of the coefficient of lift with flaps up and flaps down. As you can see, flaps allow us to maintain the same coefficient of lift at a lower angle of attack, which allows for variations in descent profiles. Or, flaps allow us to achieve a greater coefficient of lift for the same angle of attack, which provides for a reduction in approach speeds while maintaining the same amount of lift. Regardless of how a pilot utilizes flaps during an approach, it is important to determine if the angle of attack system being used is calibrated in multiple wing and flap configurations or in a single configuration. Slots or slats allow for a higher coefficient of lift at the same angle of attack because the airflow will not separate from the airfoil at the higher angle of attack. The slots or slats allow the airflow to remain attached to the surface of the wing at higher angles of attack. An AOA device would need to be calibrated for this wing configuration in order to correctly measure the angle of attack at stall, or 1.3 times the stall speed. Wing contamination of any type will affect the parasitic drag of the wing. This impact is felt by having to fly a specific airspeed at a higher angle of attack to produce the same amount of lift. The contamination will also cause the airflow to separate earlier than a clean wing, causing higher drag at any angle of attack. Calibration of angle of attack displays could be affected by wing contamination, and information presented may be unreliable if the wing is contaminated. There are two main styles of angle of attack devices. The first is a transducer style, which can be further divided into two subcategories. One subcategory is a vane style, which rotates to align with the relative wind. The other is a tab style, which measures the stagnation point of the airflow impacting the wing. The other AOA device is a pressure style, which measures the vector of the relative wind by comparing the pressure from two different ports. It is important that you're aware, based on the manufacturer of your AOA device, how the angle of attack is being measured. The FAA has disseminated a press release indicating that they are streamlining the process for approval of angle of attack equipment in various aircraft. It is important to note that within the press release, in the design requirements, the FAA has mandated that a placard be placed that indicates that the AOA system is not for use as a primary instrument for flight. Further, within the operational limitations section of the press release, they have stated that an AOA system is non-required and is to be used only as supplemental information to the pilot. It is important to keep these two considerations in mind while utilizing the angle of attack displays. Additionally, the FAA has released an Information for Operators, or INFO, numbered 14010, dated July 25, 2014, which addresses the installation, training, and use of non-required supplemental angle of attack-based systems for general aviation airplanes. It is a resource that provides important information for implementation. Here are several examples of AOA displays. Different manufacturers will have different types of displays. How the AOA functions, i.e. the transducer or pressure system, also varies by installation and manufacturer. The main takeaway from this slide is that personal preference and aircraft compatibility are the primary considerations. It is important to familiarize yourself with a variety of angle of attack displays and select the one that suits your needs the best. Installation of the optional probe heat function requires some planning. The probe heat will require a separate switch and fuse or breaker along with the appropriate wiring for the length and amount of load carried per Advisory Circular AC 43.13-1B, Chapter 11, Section 5. The probe heat requires over 7 amps of electrical power. Use shielded wire to minimize interference with other instrumentation and route the wiring such that the risk of a mechanical damage and/or damage caused by fluids, vapors, or sources of heat is minimized. Follow the installation manual and use AC 43 as discussed in the manual to complete the installation. Properly label the switch and fuse and breaker per the installation manual. Operation of the probe heat does not affect the angle of attack calculations or readings. It is recommended that probe heat be installed if the AOA system will be utilized in the IMC environment. The Alpha Systems and Bendixking devices utilize a three-part system. There is a probe that attaches to an inspection panel on the bottom of the aircraft's wing or fuselage, a computer to process inputs from the probe, which is placed out of sight, usually in the aircraft's cockpit, and the display unit. Installation is simple for aircraft with inspection panels. For aircraft without inspection panels, or that are made of fabric, installation is more complicated, but not impossible. The Safe Flight device utilizes a two-part system. There is a transducer tab that is installed on the leading edge of the wing, and the processing and display unit that is placed in the cockpit in view of the pilot. The transducer tab needs to be positioned on the leading edge of the wing and needs to have a hole cut in the wing. This becomes difficult, but not impossible, on composite aircraft. The probe used in the Alpha Systems and Bendixking devices has two ports, each intaking ram air and sending it to the processing unit. The processor then calculates the difference in ram air pressure between the two ports to determine the direction of the relative wind. The Safe Flight device has a tab on the leading edge of the wing that is moved by the relative wind to sense the stagnation point. It then sends this information to the device in the cockpit to be displayed to the pilot. While simple in theory, the precision of the device and its calibration is what allows it to measure the direction of the relative wind. The Alpha Systems device features an on-speed donut and 2 carrots, indicating what action must be taken to adjust the angle of attack. It can be calibrated from within the cockpit and gives a verbal warning when the aircraft is approaching the stall. This warning is usually in advance of the installed stall system, which gives the pilot advanced warning for stall avoidance. The device has multiple audio warning sounds, which can be selected by the pilot, which are demonstrated now.
Too slow. Getting slow. Too slow.
The Bendixking device features an on-speed donut and a stall warning arrow, indicating that the angle of attack must be reduced. It gives a verbal warning which indicates that the pilot must take action to correct the AOA. It gives a verbal warning when the aircraft is approaching stall. This warning is usually in advance of the installed stall system, which gives the pilot advanced warning for stall avoidance.
Check AOA. Caution. Too slow. Too slow. Too slow. Too slow. Too slow.
The Safe Flight device features an on-speed indicator and a series of multicolored dots that indicate whether the aircraft is over or under speed. Additionally, the device has settable bugs to be used for various different maneuvers. The device gives a Geiger counter warning when the aircraft is approaching stall. This warning is usually in advance of the installed stall system, which gives the pilot advanced warning for stall avoidance. Now we will take a look at how the devices perform in several maneuvers. In the following videos, you will see all 3 devices side by side. The maneuver being performed will be the same for all 3, and you can see an outside view for reference below the angle of attack device. When you see a green box around a device, you are listening to the audio from that system. The first maneuver we will see is a power off stall. All 3 devices perform as expected during this maneuver, gradually increasing their indication before giving a warning to the pilot.
Geiger counter. And get the brake. Lower the nose.
Now we will see a power on stall. The indications of the displays during the maneuver are very similar to the power off stall.
Getting slow. Too slow. Too slow. Too slow.
Next is a cross-controlled stall, which simulates overshooting the base to final turn. In this maneuver, the pilot presses on the inside rudder and maintains a constant bank with opposite aileron, creating a cross-controlled situation. This can quickly lead to a low-altitude stall and spin if the pilot is not careful. Again, the devices perform as expected and provide a warning to the pilot.
Check AOA. Caution. Too slow. Caution. Too slow.
Depending on the system, slips can provide very different indications. The Alpha Systems and Bendixking devices must have a clean flow of air, not obstructed by any objects on the wing. During a slip, objects such as tie-down rings or landing gear struts can obstruct the airflow and give erroneous indications. Let's see how the 3 devices indicate a slip. Let's take a look at some steep turns. Performing this maneuver with these devices is a great demonstration of how the wing increases in load factor during a level turn. With the displays, you can visually watch the aerodynamic change as the bank angle increases. This is an indication of the increasing load factor on the wing, which requires an increased angle of attack to maintain altitude. Now we will watch a normal approach to landing. Depending on how each device is calibrated and the type of approach being conducted, the pilot should aim to hold a consistent indication during the approach. The devices we are demonstrating were calibrated to approach at the on-speed indication, which provides a stabilized approach. This is one of the key benefits of these devices, as they can provide valuable information about the approach that cannot be obtained in any other way.
Too slow.
In this video, we have shown you why angle of attack devices and lift indicators have become prevalent and why they are valuable. We have also given you specific information about certain systems, but note that there are other manufacturers and systems available. The biggest takeaway from this video is that these devices can provide valuable information to the pilot during maneuvering flight and have been identified as a mitigation strategy to prevent loss of control accidents. It is important to take this information and make an informed, yet personal decision about what is the right choice for you. Every pilot is different, and every device has advantages and disadvantages for each individual and each aircraft type. We hope that we have provided you with some information that you can utilize to make your own decision regarding angle of attack devices and lift indicators.
Please direct any questions to your local FAST Team representative. Special thanks to the Jeremy Walters Band for backing music. Narration by Bradford Wood, FAST Team National Outreach Manager. There's nothing like the feeling you get when you know you're playing your A game, and in order to do that, you need a good coach. So fly regularly with a CFI who will challenge you to review what you know, explore new horizons, and to always do your best. Of course, you'll have to dedicate time and money to your proficiency program, but it's well worth it for the peace of mind that comes with confidence. Vince Lombardi, the famous football coach, said, "Practice does not make perfect. Only perfect practice makes perfect." For pilots, that means flying with precision, on course, on altitude, on speed, all the time. And be sure to document your achievement in the Wings Proficiency Program. It's a great way to stay on top of your game and keep your flight review current. Your presence here shows that you are a vital member of our general aviation safety community. The high standards you keep and the examples you set are a great credit to you and to GA. Thank you for attending.